In this video, I want to take a look at the convergence of series. How do we decide whether they converge or diverge? So here we go. I'm going to start with the geometric series because there's a fair amount that I can say about that fairly quickly here. So remember, the geometric series is one where each term can be obtained from the previous one by just multiplying by the same constant. So if I start with c and I multiply by r each time, then the second term would be c times r, and the third term would be c times r squared, and c times r cubed, and so on. Okay. Now, the question is, what does that add up to? Does it add up to something finite? Well, if it does, let's call that something s. And so what I do is I multiply both sides by r, and on the right-hand side, of course, just s times r. On the left-hand side, let's distribute that r through. So CR is the first one, and then CR squared for the second one, and CR cubed, right? Just keep multiplying by R. Just increases all those exponents by 1. Okay. Now what I want to do is I want to take this first equation and subtract this one that I have right here. So on the right-hand side, it's just S minus SR. On the left-hand side, it's all this stuff minus all that stuff. Well, the minus all that stuff is essentially distributing a minus 1 into each of those and then adding them here. So I've got a C and I've got a plus CR, but then I'd have a minus CR, and I'd have a plus CR squared, and I'd have a minus CR squared, and a plus CR cubed, and a minus CR cubed. In fact, every single term here would have a negative, well, almost every single term here would have the appropriate negative canceling it out. The only one that doesn't is the initial C. So the only thing that's left is just the C right there. So C equals S minus SR. I can now solve for S, factor out the S, and divide by the R minus 1. So S is equal to C over 1 minus R. Okay. This is the process I knew how to do when I was 10. My dad had showed me how to do it. It was really cool. I could add up these infinitely long things, and yeah, it was amazing. So when we did that, had that ice cream that night, and I needed to figure out how much each person had, this is what I was about to do. I was going to do this whole process and figure out what it was. And so the thing is, 1/8. So 1/8 is being used as C and it's being used as R here because it's starting at 1/8 and I'm multiplying by 1/8 each time. So the C is 1/8 and the R is 1/8, and it ends up being 1/7. Everybody got the same amount of ice cream, and we were 7 people. Okay. Now, there's a couple of issues with this process. Right. Here we go. What are the problems? One, we started with the assumption if it adds up to something. But what if it doesn't add up to something? Then everything we just did is out the window. It doesn't apply, right? If you start with a false assumption, you can conclude anything you want, and it's meaningless. Okay, so if this did add up to something, then it adds up to that formula that we got. Okay, if it doesn't add up to something, then this formula is meaningless. Now, notice, for instance, if r is equal to 1. Well, if r is equal to 1, then you got a vertical asymptote here. You got a c divided by 1 minus 1, and that's a problem. But then if r was equal to 1, where's the original thing here? If r is equal to 1, this would be c plus c plus c plus c. Yeah. You've got c's all the way from here to, I would say, from c to shining c. That's not a finite sum. That's definitely an infinite sum. That does not add up to something finite. Okay. Unless, of course, c was 0, and then it adds up to 0, but then it wouldn't really be very exciting if c was equal to 0. Also, we got issues when r is bigger than 1. Because, for instance, let's start here with c equals 1 and r equals 2. So 1, 2, multiplied by 2 each time, 4, 8, 16, right? This is powers of 2 being added up. According to the formula, it should be 1 over 1 minus 2, which would be negative 1. What? There isn't any way that 1 plus 2 plus 4 plus 8 plus 16 is equal to negative 1. It doesn't work. The thing is, this does not add up to something finite. Remember, the way we add up the infinite sum is we look at the partial sums and look at the limit. So the first partial sum is 1, the second partial sum is 1 plus 2, which is 3, 7, 15, 31, right? You keep adding on that next term and saying does that sequence of numbers have a limit? And the answer is no, it goes to infinity. This does not add up to something finite. Okay? So if r is bigger than 1, what's going to happen is that each term is going to be bigger than the next term, and it won't add up to something finite. Okay? If r is less than 1, on the other hand, they get smaller, like these did. Now, also there's the issue of r negative. We really only talked about positive r's here. So for instance, here is using c equals 1 and r equals minus a half. So minus a half plus a fourth minus an eighth. I keep multiplying by negative a half each time to get to the next one. Now this, in fact, does add up to something finite. It adds up to 2/3 according to the formula, and I would say according to other ways of thinking about it. And I'm going to click on this link to see another way of thinking about it. Okay, so here is a square. Let's say that that big square is one piece of pie. So I'm going to take that whole pie and then say, well, I don't need to eat the whole pie. I'm going to throw away half of it. So everything on the left-hand side gets thrown away. But then it's like, nah, maybe I do want to eat half of that. So I had a whole and then I threw away half, but I'm going to add back in, I'm going to add back in a quarter. So I'm going to add back in this stuff, and then I'm going to say, no, I don't need all of that stuff. Throw half of it away, right? So I'm throwing away this half, and then I would say, oh no, add back in half of that, and then no, throw away half of that, and then no, add back in half of that. So what happens is that what ends up, this was in from the beginning and stayed in. This got thrown away, but this got added back in, so this is now in, and that this got thrown away, and this stuff got added back in. So these rectangles here are what are left over in the sum, and this stuff is gets thrown out. And I claim that the sum of these rectangles is 2/3 of the whole thing, because, well, look at here. This square is half of this. So this rectangle is twice as big as that, and this rectangle is twice as big as that square, and this rectangle is twice as big as that square. So on each one of these L's, 2/3 of the L is in the sum and 1/3 is out. So if the total is 1, then what I have is 2/3 of that rectangle. Okay. So yeah, it adds up to 2/3. How about if r equals, so that was r equals minus a half, how r equals minus 1? Look what happens at minus 1. Start with 1, and then multiply by minus 1, and then multiply by minus 1, and then multiply by minus 1. So the terms keep alternating between 1 and minus 1. Right? What does this add up to? 1, minus 1, plus 1, minus 1, plus 1, minus 1. It's really easy to say, this should add up to 0 because the 1 minus 1, and the 1 minus 1, and the 1 minus 1, they're zeros. But remember, the way we add these up is we do it term by term. Start with the first term, 1, add the next term, minus 1, add the next term, plus 1, add the next term, minus 1. So the sum goes from 1 down to 0, to 1, down to 0, to 1, down to 0, to 1, down to 0. The partial sums keep alternating back and forth between 1 and 0. So is there a limit? The answer is no. The formula here, if you plugged it in, you plugged in a 1 over 1 minus minus 1, it would give you a half, 1 over 2. It says that this should add up to a half, which in some ways kind of makes sense because it alternates back and forth between 0 and 1, so kind of on average it's equal to a half, but it's never equal to a half and it doesn't get close to a half. But anyway, this diverges, right? For r equals minus 1, this diverges. And likewise, try r equals minus 2. Starting at 1, multiply by minus 2, multiply by minus 2, multiply by minus 2, add all those up, right? So I've got 1 minus 2 plus 4 minus 8 plus 16. So look at what happens. So 1 minus 2 is minus 1. Add 4. 4 would get me to 3. Subtract 8 minus 5. Add 16. What's that? 11. Subtract 32. Right? It's just alternating back and forth. The positive number and negative number getting bigger and bigger further away from 0. This does not converge. Right? The net result is that a geometric series converges when r is less than 1. The absolute value of r is less than 1. So for small r's close to 0, you get these things. And actually, when you think about it, with r less than 1, right, each term is getting smaller than the previous term, right? Because you're multiplying by r each time. If I multiply by a small number, something less between 0 and 1, I get a smaller result. And the absolute value being less than 1, absolute value of r being less than 1, means I can use negative numbers too. So I might have alternating plus or minus signs here, but the magnitude of each term would be getting smaller and smaller. Okay. Once you get r bigger than 1, then each term is getting bigger and bigger, and the series diverges. Okay. Alternating series. We did see some alternating series here in the end, and there's actually a nice way of checking whether alternating series converge or not, because the alternating series test says that if the terms are going to 0, that the limit of the ANs is 0, and eventually they're decreasing, eventually each term is smaller than the previous one, then you're guaranteed that this will converge. For instance, here's what's called the alternating harmonic series. 1 minus a half plus a third minus a fourth plus a fifth minus a sixth. That is, you got an alternating plus or minus sign, and the denominators are just n, right? 1 over n. And here's a visual of this. So I've got 0 here and 1 right there. So the first term is 1. And then I add on negative a half, which would get me to here. And then I add on a third, which gets me to there. And then I subtract a fourth, and I add a fifth, and I subtract a sixth, and I add a seventh, and I subtract an eighth. The thing is, each time you're moving in a different direction, right? The first time go from 0 to 1, I move to the right. And then from 1 to a half, I move to the left, and then to the right, and to the left, and to the right, to the left. So you keep alternating back and forth which direction you're moving. And each time you move a smaller amount than you did the last time. So once you know that you're somewhere between here and here, you know that the next one is not going to be outside that range. It's going to be somewhere in here. The next point then would be no further to the left than that one was. And as long as you know that the limit of all of them is 0, so that you're going to be adding on less and less and less each time all the way down to 0, then eventually this will converge to a point. It's not at all clear what the value is necessarily, but I know that this converges. Now, I happen to also know that this converges to the natural log of 2 for other reasons. And we will see those other reasons eventually at some point in one of these videos. Absolute convergence. Okay. One more thing I want to talk about before power series, and I'll do power series in the next video, is the notion of absolute convergence. A series is said to converge absolutely if this series converges. Okay. So this series right here might have pluses and minuses, like this one right here, right? The ANs here are what, minus 1 to the n times 1 over n. Okay. And so that the ANs are alternating signs. Okay. When I take the absolute value of all of those terms and add them up, then everything's plus. Okay. So this one might have pluses and minuses. This one has all pluses. And it's harder to get all positives to add to something finite than it is to get positives and negatives to add up to something finite. Okay. So we say it converges absolutely if you take the absolute value of all the terms and add it up, and that still converges. Okay. For instance, this alternating series right here, 1 minus a half plus a fourth minus an eighth, this does converge absolutely, because if I add them up as all positives, 1 plus a half plus a fourth plus an eighth, this adds up to a finite number. In fact, it adds up to 2. I see this as ice cream again. I sit down, I eat a whole thing of ice cream, and then I say, I want a little more. So I grab another thing, and I say, I don't need all of it, I'll just eat half of that. And then I get done with that half, and I say, I'll just eat half of that, what's left, and so I have the fourth. And then I say, let me just eat a half of what's left, and I eat an eighth. So I eat a 1 whole, and then I eat a half and a quarter and an eighth, and it turns out I eat that whole second container of ice cream, and so it adds up to 2. Right? This adds up to 2. Finite. This converges absolutely. It converged to 2/3, and it converges absolutely because when you turn it into all positives, you get another finite number, in this case 2. The alternating harmonic series, on the other hand, does not converge absolutely. We saw that it converged. The value is natural log 2. But it does not converge absolutely, because when I make them all positives, 1 plus a half plus a third plus a fourth and so on, this does not converge. This is not immediately obvious because they definitely are getting small. All of those values, each one is smaller than the previous one. But I can show you that it diverges by comparing it to the following. Each term in what I have listed here is going to be smaller than or equal to what was above here. So this sum down here will be a smaller sum than the one above, right? So the 1 I'm leaving the same, the half I'm leaving the same. But I'm going to turn that 1/3 into a 1/4. So this 1/4 is smaller than the 1/3, right? The 1/4 I'll leave the same. 1/5 I'm going to turn into a 1/8. 1/6 into a 1/8. 1/7 into a 1/8. 1/8 I'll leave as a 1/8. Once I get to 1/9, I'm going to switch to turning that into a 1/16. And I'll do that until I get to 1/16 will turn into 1/16, and then the 1/17 will turn into 1/32, right? And then look what happens here when I add this up. This is 1 plus a half plus a quarter plus a quarter. Well, the quarter plus a quarter is a half. And then I have plus an eighth, plus an eighth, plus an eighth, plus an eighth. Well, 4/8 is another half. And then I'm going to have a 16th plus a 16th. I have 8 16ths here, which is also a half. And then I'm going to have 16 32nds that I add on. And then I'm going to have 32 64ths that I'm going to add on. And so this is going to be a half, sorry, 1 plus a half, 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 infinitely. And that adds up to infinity. This diverges, and this is bigger than that. And so this also must diverge. Okay. So when you have a series like that, that converges, but does not converge absolutely, we say that this is conditionally convergent, right? It converges conditionally. Yeah, it converges, but not if you had all plus signs. Okay. Now, we need to talk about power series and their convergence, but I think we will do that in another video.